You guys can hear me good? Okay, cool, thanks. Yeah, so thanks for the organizers for the invitation. It's been really fun hanging out with friends and hearing about all their recent physics results. Today I'm going to talk about kind of old work with Dimitris. This came out last year. It's on gravitational self-force and scattering amplitudes. And maybe, I don't know if I'll have time, but I'll at least mention where this is headed. And this is work in progress with a student at UCLA. His name's Mikhail. Okay, so as we've probably heard in some of the talks, there's very great success of applying quantum field theory tools for gravitational waves. Okay, so one of the things that we want to describe when we talk about gravitational waves is the dynamics of binaries. And here, for example, is a cartoon of a binary. One black hole with mass capital M and, one black hole with mass lowercase m separated by a distance r. And here is a phase space diagram of various methods that people use in general relativity to describe the dynamics of this binary. So when the mass ratios, for instance, are of order of each other and the binaries are close to each other, then what we use is numerical relativity. On the other hand, when the binary constituents are far apart, and depending on how far apart they are, then we have a weak field approximation. And there we use the methods of post-Minkowskian or post-Newtonian formalisms. And so far, quantum field theory has been really successful in producing or also checking results in this regime. So everywhere above this line is where quantum field theory does well, at least so far. But as we've heard already from Julio, for example, there are these new interesting directions where merged with some information about black holes, we can start to combine these tools. And so naturally, there's a question. Oh, by the way, let me mention that I'm jumping straight right in here. If you want a review of applications of quantum field theory, effective field theory, and amplitudes to gravitational waves, you'll unfortunately have to wait till Friday for Radu's talk. But here I'm just jumping straight in. So there's a natural question then of whether we can apply quantum field theory in this other regime. So in this other regime, the mass ratios is quite large. So this is describing the in-spiral, or what is called an extreme mass ratio in-spiral, where one of the black holes is very big and one of them is smaller. Okay? And so today I will talk to you about, so the builds are not showing up in my PDF for some reason, so I'll just have to roll with that. So why do we want to apply quantum field theory for gravitational self-force? Well, this region in particular is very interesting for LISA, and we need predictions for LISA precisely in this regime. And even if there are methods based on general relativity for describing gravitational self-force, what we've learned in applications of quantum field theory in this regime, for example, the post-Minkowskian approximation, is that synergies with existing methods are very important. So a lot of the developments that happened in this regime right here is because of merging of two tools, or at least even like two approaches. An example of this, just to mention, is something that's called the tutti frutti method by Damour, which takes as input various things, okay? Also, of course, EOB, for instance. And finally, as I'll mention in more detail later on, quantum field theory is, as we've been applying it to this regime, is not quite enough, or is doomed to fail at least, if we want to go to this regime. And so pushing quantum field theory in this new region provides an opportunity to perhaps learn about quantum field theory. Okay, so as I said, what will be described in the talk is based on previous work with Dimitris. He's an excellent postdoc at Geneva, is on the market this year, and also ongoing work with a student at UCLA. When our paper came out, there's also a series of papers from the Caltech group. Some of Julio, for example, is here. So I encourage you to look at their paper as well for a complementary approach. Oh, wow. Yes, these are my older slides. No, it's okay. This wasn't supposed to appear until a later slide, but it's okay. It's right here. I already alluded to the fact that in order to bring quantum field theory in this regime, we really need to incorporate information about black holes. And I'm very excited to hear Julia's talk on Thursday, which is a very, very interesting example of merging basically tools from quantum field theory and tools from black hole perturbation theory to describe new results. Okay? And as we already heard from Julio, and another talk to look forward to in that regard is Zihan's talk. Okay, so as I mentioned, quantum field theory methods are perturbative and well suited for gravitational waves. In particular, in that regime, there are a various number of small parameters. For instance, the Planck mass over the masses of the binary constituents is really small. This would be something like 10 to the minus 38. H bar is a much, much smaller angular momentum than the angular momentum of the astrophysical objects. And so in this limit of large charges, that's how we recover basically the classical limit of amplitudes. Another small parameter that we use is, of course, the fact that the binary constituents are far apart, and really we can think of this as a weak field expansion. Okay? So the Schwarzschild radii of each of the bodies is much smaller than their separation. And finally, if we wish, we could also derive results that are non-relativistic by just expanding in velocity. Okay, so as I said, a real full-fledged review of this will be given on Friday by Radu, but here let me just recap it with sort of the slogan of how this thing is done. Basically, the idea is to perform Rutherford scattering experiment. So Rutherford scattering experiment is you put a gold film and you bombard it with alpha particles. You measure the scattering angle, and from that you can reverse deduce the potential between the particles that make up those two materials. Of course, we can't do that with black holes. We can put a black hole in the laboratory and scatter another black hole with it. But the interesting thing, or one of the main results of this program, is that this scattering angle actually is just a logarithm of the amplitude. So you compute the 2-to-2 scattering of the amplitude, take the logarithm, and that would be the scattering angle. And so that's how you go from an amplitude to something that actually has to do with literally the classical dynamics of the system. Rose. Okay, but gravitational self-force, on the other hand, is not perturbative. So we still are interested in charges that are large because we're interested in classical dynamics. But in particular, we don't have weak fields. If you remember in that phase diagram, we're interested in a region where the two bodies are actually close to each other. Okay. Now, whether we expand it non-relativistic or not is not so much important, but really the main point here is that we want to capture an amplitude to all origin g. Okay, so instead of the usual expansion of an amplitude in terms of the coupling, here we see that the amplitude is expanded in terms of the mass ratio. So this is the small parameter that we have in gravitational self-force. So just writing out the first few terms and calling, calibrating this to 0 SF. There are some overall prefactors here that I have not written out, but the first term would be 0 SF. The second term would be first order and self-force corrections, and so on and so forth. If you're used to thinking in terms of flat space diagrams, then this set of 0 SF graphs are really these graphs where on the side of the light particle, there is no propagator. Okay, so on the other hand, on the side of the heavy particle, there's as many propagators as you want. So this function here really resums this class of diagrams, which sometimes are in the literature are called fan diagrams. On the other hand, at 1 SF order, what you're resumming are these graphs with a single propagator on the side of the light particle and as many propagators, again, on the side of the heavy particle. And so the pattern is no propagators for 0 SF, 1 propagator for 1 SF, 2 for 2 SF, and so on and so forth. And so if you can imagine being handed this task of actually computing all this, then this is why gravitational self-force is hard. Comparing to the post-Minkowskian expansion, so the post-Minkowskian expansion, yeah, okay, sorry, this is an older slide. There should be stuff in here. But okay, so let me just say it in words then. So in the post-Minkowskian expansion, the amplitudes are expanded in fixed order G. So this would be 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m., and so on. And how gravitational self-force intersects with post-Minkowskian is that if you look at the limit of large M1, so previously in my slides I've been using capital M and lowercase m. Here the large mass is M1 and the small mass is M2. Then 0 SF would be this tower of corrections right here in this first column. And then 1 SF would be this tower of corrections right here in the second column. And then 2 SF would be the next tower of corrections. And why this is a powerful method in terms of PM is because if you know 0 SF, actually you know 1 PM and 2 PM, because this term here is just given by symmetrizing the labels of the masses. If you know 1 SF, then you know all the way up to g to the 4, because you know these first two terms, and these last two terms are just given by symmetrizing the masses. And in particular, if you know 2 SF, then you also know up to g to the 6. And so this intersection between SF and PM is very interesting. And even if you're interested in PM, thinking in terms of SF is actually useful. Okay, but I said gravitational self-force is non-perturbative. In particular, there really is no, at least I know of no direct analog of an expansion in ratios of charges in QFT. Of course, the closest expansion you might think is just the heavy quark expansion, which expands amplitudes in 1 over m. But even the heavy quark expansion in QCD would be an expansion in 1 over m, but also an expansion in a weak field, so small alpha s, of course. And in particular, that expansion in 1 over m is not really just ratios of charges, but also includes momenta and so on. And furthermore, the resummation of this is not something that we really know. It's not an RT resummation, for example. It's not a regization of something, and so on and so forth. Okay. So this is what I meant by using QFT in this regime is quite interesting, because it's very different. It's unlike the application to PM, where things were not to say obvious, but at least very well suited to perturbative methods. On the other hand, gravitational self-force is really more natural in Einstein's theory. Okay, so in particular, Einstein's theory, of course, we know about black hole solutions. On those black hole solutions, we know about geodesic motion. So this would be, for example, the motion of the light particle about it. And in fact, at 0 SF, we would really be just expanding about the geodesic of a light particle about black hole spacetime. And finally, and important for making progress here, is that we also know through, for example, the Tucholsky equation, how to perturb about black hole spacetimes. Okay? And so a lot of us here in this room have spent time thinking about perhaps how to apply tools of quantum field theory to Einstein's theory. But this is really an example where we really also need to think in terms of the other direction. Okay, so there is this virtuous cycle between the two. And as I said, a nice example of using tools from both and getting new results. If you want, you'll see it in Julia's talk on Thursday. Okay, so what is the idea? The idea is then, instead of doing Rutherford scattering with this heavy black hole, what we do is we take away this heavy black hole and replace it with a background geometry. So then the action is just now the action for one point particle, and also the gravitational Einstein-Hilbert term, but expanded about the black hole spacetime. So in the correct version of the slides, there's a next button which deletes this black hole here, and you would just see this probe particle orbiting in this spacetime. Okay? And for now, we're really interested in the far zone effects, no horizon effects, and but in principle, it would be interesting to capture horizon effects, as I'll mention later on. But for now, it's a very it's a calculation that's made clean, because by design we are basically capturing the flat space limit. Okay, so in other words, this expansion is really an expansion about the flat space limit. For the experts in the audience, for example, when we solve Tucholsky, then we would use the same boundary conditions that reduce the flat space and so on and so forth. But of course, as you know, a lot of the interesting stuff in the solution really has to do with the near zone. So in current work, that's what we are explore. Okay, so what are the observables in this theory? Usually, as I drew Feynman diagrams early on, we're thinking about 2-to-2 scattering or the 4-point amplitude in flat space. But we've removed the heavy particle, so there really is no Fock space for that particle. Instead, we just have a curved geometry. And so the natural observables now are 2-point functions in this curved space, okay? Which, of course, in QFT would be called self-energy. And so this set of graphs is what we're interested in. And one thing that's nice that comes out of this formalism immediately is that if you power count the m over m, small m over capital M scaling of these graphs, then you find that the self-force power counting is just given by the number of loops. So for instance, this piece right here is just the 0 SF graph with 0 loops. This piece would be the 1 SF graph with 1 loop, 2 SF with 2 loops, and so on and so forth. Okay, so it's really organizes things now in terms of the small parameter that we want to organize the amplitude. Okay. Okay, so how do we actually compute this? Well, like I said, ideally, we'd like to use propagators in the black hole background. And a propagator in the black hole background, you can construct, of course, you compute a 2-point function, and that 2-point function is constructed in terms of solutions of the Kolsky equation. And so that is something that Mishari has been working on. In the previous paper, as a first pass, what we've done is just expand the propagators about flat space. Okay, so as I'll show you, this is good because it tells us that we're on the right track, we get the right results, but it's not good because you don't really get to do gravitational self-force. You just rederive PM in a different way, and that's not what we want to do here. Nonetheless, it teaches us a few things. So, for instance, the 0 SF amplitude is just a bunch of tree-level graphs, or there's no loops here, so I'll call them tree-level 2-point functions with insertions of backgrounds. And each vertex here is all orders in G, and in particular, you see here the dependence on the metric. This is the part of the action whose Feynman rule gives that vertex. And if you do this just by brute force, doing 1 insertion, 2 insertion, 3 insertion, 4, and so on and so forth, you just notice that it resums as a geometric series. And so you can just do this directly by hand, resum it as a geometric series, and you get the correct 0 SF amplitude. We know what the correct 0 SF amplitude is because we can, for example, reverse engineer this from the scattering angle of a probe particle. Okay? And so just as a reminder, this result really resums this set of flat space diagram. As a check, and also because we're interested in really resumming these graphs in a more elegant way, one thing that we did was to perform a field redefinition. And in this field redefinition, these multiple insertions actually give nothing but the iterations. So remember, we are interested in the logarithm of the amplitude, and a bunch of these contributions are just redundancies. They're just iterations of previously computed contributions. And so in this new field basis, this whole thing reduces to just a single insertion. Okay. Now that we understand geodesic motion, it's nice to mod it out. So in HQET, we want to expand the momentum of the heavy quark about a large piece, which we call MV, which, by the way, is a geodesic in flat space, and then describe the dynamics of that heavy quark in terms of just this small residual momentum. Okay, and we do that by performing this field redefinition. We basically absorb out this large momentum from the mode expansion. Okay, and so then the heavy quark field would just be given by this curly phi. Similarly, we can mod out geodesic motion, and that's interesting to do here because then you don't have to deal with those insertions every time you do a loop. Everything is just factored out such that when you compute any kind of correction to the two-point function, it's immediately a self-force correction. And you do that by a similar rephasing, but this SP here is really the classical action. So if you want the analog of this would be P is equal to partial SP plus K. And so the idea of taking out the geodesic piece is that now you're just describing field theory about the geodesic. Okay, and you can compute corrections about that geodesic without having to insert that geodesic everywhere else. Okay, so this is the rephasing. This rephasing, of course, obeys this, which is just, if you think about each of these factors as P mu, then this is just the geodesic equation. And you can, in fact, solve for SP to your heart's content to however high power of G. Okay, so this is how we, at the end of the day, can resum the geodesic motion or those insertions of the background. Okay, so beyond 0SF, there is, in this way of expanding about flat space, we have to deal with the fact that the black hole recoils. So at 0SF, you're really talking about the geodesic motion of a probe particle. And this probe particle doesn't influence your black hole. And so it makes sense to have it in the action as just a static background. But beyond 0SF, this probe particle starts to kick your black hole, and the black hole recoils. Ideally, if we had solved for the graviton propagator from Tucholsky, presumably this is already inside that solution because, for instance, the boundary conditions of the near zone would know about perturbations of the black hole, including these kicks. However, since we expanded about the flat space propagator, so here this is a full theory propagator in the background expanded about flat space. So here we have the flat space propagators plus interaction terms. Then we've lost any input from boundary conditions at the horizon. And in particular, this doesn't describe recoil. For instance, we know this because just computing, for instance, the Compton scattering with one of these vertices inserted would not give you the right result. So this would be the Compton amplitude, and just with this piece doesn't give you the right result. The resolution is to include by hand the goldstones of space-time symmetry breaking. So putting the black hole at an origin basically breaks space-time translation, and the goldstones of that are light degrees of freedom that you must include in order to describe these deflections. Okay. And so here you have the goldstone contribution, and here I'm just showing you that there's an action for this goldstones. In particular, these are the Feynman rules. Okay, so what are checks of this idea of including the goldstones? Well, if you compute the Compton amplitude, now it works out. We also computed the graviton emission. So this would be a 5-point amplitude in flat. Remember, there's a 2 points missing because we've deleted the heavy particle. And now, crucially, with that goldstone contribution, things work out. Okay, so with all the pieces together, we can now compute, for example, 1SF truncated to some G power. Here, we just went up to G cubed because life is short and we want to do other things. But in principle, all the pieces are here to systematically go up to some high G power. And we indeed check that this reduces to the correct answer. Again, as I said, this formalism that we explored we aren't really interested in developing PM again, but it's worth noting, though, that there are some advantages if you were interested in using this to compute PM. For instance, even though the propagators are expanded above flat space, there is partial resummation. For example, at the vertices, there are Eulers and G functions that you get for free. And also, because the black hole is not really a propagator that you end up cutting and then marrying with other graphs to form Sturman combinations, all Sturman combinations this is a little technical point for the experts, but Sturman combinations are automatic in this framework. Okay, so that makes integrands somewhat easier. Okay, so with geodesic motion under control and expanding about flat space under control, in future work, what we really want to do is really include the graviton propagator in a non-trivial background. So as Julio rebranded this thing, let's call it the Raman scattering amplitude instead of Compton. And the main point is that this would include, for example, the tree level piece, the goldstone, higher loops, love numbers, dissipation, and so on and so forth. So you can imagine that if you use actually the full information from Tucholsky, then you would get all of this for free in 2-2-2 scattering. So instead of parameterizing, for example, love numbers as a free parameter, putting it into 2-2-2 scattering, computing an amplitude, and then separately fixing that to Tucholsky, everything now, these propagators would depend on the solutions to Tucholsky. So specifically here, I just mean you write the propagator in terms of solutions of Tucholsky. Okay. And one nice thing is that a lot of these loops, as we've said, is really just not, these aren't loop calculations to do, but rather just the integrals that are already done for you if you know the solutions to Tucholsky. Okay, so these integrals are just iterated to get the solution to Tucholsky, and really the loop that you need to do is the last loop right there. Okay, so I think I probably have no time left, so, 4 minutes, okay, but this is all I have to say. So the outlook is that I hope I've conveyed to you that applying quantum field theory to gravitational self-force is an important problem and also an interesting problem. It would, for example, allow us to make predictions for LISA that we currently do not have. It would allow us to develop new tools that can be merged with interesting tools from black hole perturbation theory, for example. And I think ultimately also, if you're a fan of QFT, then this would probably teach us something about QFT. Okay.
Thanks, very interesting talk. Is there any questions?
You touched upon horizon effects, saying that we neglect them. Can you briefly mention them?
I just mean that, for example, I'm not interested in putting Hawking radiation in my calculation, which you might think of that as an example of a QFT curved space effect. It is a QFT curved space effect, but to describe that, you would actually need a metric that goes past the horizon. And of course, that leads to particle production because of different states in different regions of space-time. Here, we're not interested in that. We're interested in spacetimes that have a time-like killing vector such that the states are always the same, in and out. And also asymptotically flat. Basically, the boundary condition is we are starting off such that we reproduce results in flat space. But there are horizon effects that we want to capture, such as, for example, just the boundary conditions at near horizon where, for example, you would be sensitive to love numbers, dissipation, stuff like that, but not Hawking radiation.
Yeah, hi, Fabian here. So I have a very basic question. So you mentioned in the 0SF, by doing like a field redefinition, you can rewrite all of this bunch of diagrams in one single term. Is it equivalent to rewriting, say, the Schwarzschild metric in Kerr-Schild coordinates, and then things become just very simple?
That's a good question. I don't know at the top of my head if there's a relation to the Kerr-Schild metric. This calculation was done in isotropic gauge, and it's really a redefinition of the field phi and not the coordinates. So I'm still in isotropic gauge, not in Kerr-Schild.
So the boson which appears as a result of the symmetry breaking, if you have a binary system, there would be two bosons, or?
Oh, instead of a black hole?
Yeah.
So binaries are complicated. Let me think of it quickly as maybe a spinning particle and a position. So the fact that it still breaks translation, you'd still have these goldstones, but you'd also break, because now you have a preferred angular momentum. So you'd also break You'd have extra gold zones if you had a spinning particle, which I'm just proxying as a binary. So yeah, you would have extra gold zones. For sure.
The gold zone for breaking of translations, etc. It's just a word line, right?
It's just a word line.
So
So
you're
the
just
closed
writing-
construction reduces to the word line.
Okay, great, thanks.
All right, I think it's time to move on. So let's thank Mikhail again.
Thanks.